All right, class, we're going to quickly talk about work and energy, review some things we've already mentioned, and then maybe touch on some new stuff a little bit. So work and energy, touch on that before exams. Um, Work is the, well, I guess first let me say what energy is. Energy is the ability to do work, and work is essentially the transfer of energy. It's like using work. Okay, the two terms don't mean the same thing, but they're very, very closely related. Okay, you did that Twinkie article. What that was is just, kind of talking about calories in and out, and that energy always has to be coming from somewhere. It always has to be going somewhere. Okay, the energy that we use has to go somewhere. When we do work, we use that energy. We give something else some kind of energy. If you think about all the different sources of energy, like you see here, windmills are moving. They move because the wind moves them. So you've got kinetic energy of the wind turns to kinetic energy of the windmill. And we use that to, turn a magnet around a copper coil. That generates electricity. But interestingly enough, it's useful to talk about the flow of energy between systems. On Earth, all the different forms of energy that we use, whether that be fossil fuels like coal, gas, and oil, or solar energy, or geothermal energy, or hydroelectric energy, almost all of those come directly from the sun. Well, indirectly from the sun. Say something like a piece of coal. The majority of electricity in the United States is still generated by burning coal. Burn coal, like you burn wood, that heats water. Heated water makes steam. Steam rises, turns a turbine. So coal has energy like stored inside of it. We call that chemical potential energy. But where did it get its energy from? Coal's a fossil fuel. It's called a fossil fuel because it comes from dead organic matter that lived and died millions of years ago. From like the seafloor, dead material, dead, sea life that accumulated on the seafloor, or in like really thick, dense jungle floors, that kind of stuff. It's called a fossil fuel because it used to be this organic stuff that got its energy through photosynthesis from the sun. So when we burn coal, we're literally reusing energy from the sun that rained down on Earth millions of years ago. And so sun came to plants on Earth millions of years ago. Those plants, through the process of photosynthesis, stored that energy. They died. They got buried. Over time, heat and pressure turned that into coal. Then we burn it. We release those that chemical potential energy stored in those bonds, and we have heat, which creates the process of seizing out. So coal, our electricity, is really powered by the sun, even though we're not really using solar power per se. But almost everything on Earth, wind comes directly from the sun. Heat patterns, hydroelectric energy, like water behind a dam, that gets traced back to the sun. Almost everything, except for geothermal and nuclear energy, all really gets traced back to the sun. And we can talk more about that later on, but it's really good exercise in just understanding the flow of energy through systems. So, energy cannot just disappear. It always has to go somewhere. Important law of physics, conservation of energy, is that energy can neither be created nor destroyed. It just goes from one thing to another thing to another thing to another thing. So when we do work, we move things, change things, crush things, kill things, move things, alter things in some shape, way, or form. So it's important to remember that. Sorry, I'm going to go a different view here so you guys can see a little bit better. But we know that energy is the ability to do work. Okay, work is a transfer of energy. When you do work on something, you're taking energy from you and giving it to there. This little idea here, that work's equal to change in energy, we call that the work-energy theorem. So, we can do work one of two ways. We can do work against another force, like gravity or friction. Against gravity to lift something, against friction to push something across the ground. Or we can change an object's speed, thereby increasing its kinetic energy. All the different types of energy we have are just different types because, why are they able to do work? Why are they able to move things, crush things, kill things, alter things in some shape, way, or form? Is it because of its speed, its position, because of the nature of its chemical bonds? What is that reason? So that's really just the whole functionality behind the types of energy. Okay, our base equation for work is force times distance. A force has to make an object move over some distance. But that's also equal to a change in energy. Work is equal to a change in energy. Work as well as energy is in the unit joules. So we push, it moves a distance, boom, work's done. Work is also done because we know that this object sped up. It gained energy, so work had to be done. Again, we're using the units joules. So joule is a very small unit. We can see that down here, very small unit of energy. But, this isn't super important. But it's important to get a little bit of a scale for it. But 1 joule is only like if we lift an apple a height of 1 meter. So not really a whole lot of work happening on with just 1 joule. Another unit for work, of course, is calories. A calorie is even a smaller unit. And believe it or not, the calories you see on food are actually kilocalories. It's just kind of hard to say thousands of calories all the time. So, but yeah, as we saw in that Twinkie article, calories is just an alternative unit for energy. But we in physics class like to use joules. So these examples over here are kind of important. So we push this way and it moves this way. We did work on the object. Let's say we're carrying this backpack. We're carrying it, so we're applying an upward force, as we see here. But we're walking with it this way, didn't do work. These 2 arrows have to be in the same direction, or at least in the same dimension. Lifting the groceries from the floor up, both in the same direction, have work. But if we're just holding the groceries and moving them this way, if these 2 arrows are perpendicular to each other, not work being done. So not only does motion required for work to be done, it's the force has to be, at least some part of that force has to be in the same direction. So like here, we're applying kind of a diagonal force here. The object's moving this way. This force has a component that's horizontal, so still work. But when we do that FD equation, we have to find the horizontal component, Fx, which would be found by F cosine of theta. To get the work, we have to multiply that by D, and we get this equation, F cosine of theta D. Or if we sum that up, we get this guy here, FD cosine of theta. Just move my little laser guy here. And this equation always works. If F and D are in the exact same direction, theta is 0, which means cosine of 0 is 1. So, and if F is up and D is horizontal, that just means that cosine is 90. What's cosine of 90? That's 0, and that makes the whole equation 0. So that means no work is done. So, important slide. Work, and we haven't talked about one aspect of this yet. Work can be positive, negative, or 0. It's positive when F and D are in the same direction. This force here has a component that's in the same direction as D. So F is positive, D is positive, that makes F times D positive. Here, F is vertical, D is horizontal. Theta winds up being 90, so that means cosine of 90 is 0, whole thing is 0. But down here, this is one case that we haven't gotten to yet, is where the force is, part of that force is acting opposite the motion. It's kind of resisting that motion forward. This is where we get negative work. The horizontal component of this force is negative, and the displacement here is positive. So a negative times a positive means negative. Now what would this mean towards what's happening to the object? That would mean that we're taking away energy. The object's trying to move this way at a certain speed. You have an opposing force like friction. You're losing energy. Here, if we're pushing in the direction of motion, that means it's speeding up. That means it's gaining energy. So since work is equivalent to a change in energy, when we have a positive work, what's a positive change mean? It means a gain. Same thing for a negative. Okay, since work is a change in energy, what's a negative change? That means a loss. Okay, and that's exactly what that means here. So negative work means a loss of energy. Things like friction do negative work. Air resistance does negative work. Positive work, any applied forces, there's all kinds of examples with that. So multiple things can be doing work on an object at the same time. Say you're pushing an object going forward, but friction, so you're pushing a crate across the floor, but friction is also acting on the object. That's acting in the direction opposite. So the work done by you. So the force, the applied force from you, multiplied by the distance of you, plus the negative work done by friction, multiplied by the distance it was acting on. And the total amount of work is going to be equal to just the sum of those. And it's a scalar sum, not a vector sum, so you don't have to worry about all that messy vector stuff. So, important ideas I've already mentioned. Amount of work done is equal to the change in the object's energy. Do work, the amount of work is the change. Change, 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 work, work, work. Simple examples, push a shopping cart, your work, you're doing work to increasing the car's kinetic energy. The amount of work is going to be equal to how much kinetic energy the cart gained. Alternatively, when you climb a mountain, you're doing work on yourself to increasing your potential energy. You're at a higher height. You have more gravitational potential energy. Work is a changed energy. So kinetic energy is the energy of motion. Potential energy is the energy of position or condition. So I'm going to skip through a few slides. It just shows you how we derive something here. But I know we've talked about kinetic energy before, but here's our equation for kinetic energy. This is your energy of motion. 1/2 mass times v squared. Okay, we're going to get to this guy up here in a second. But let's just focus on the equation for kinetic energy. 1/2 mv squared. Important thing to notice here. Square relationship between speed and kinetic energy. Test question I could ask. How much more destructive is a car crash at 40 miles per hour than one at 20 miles per hour? Well, 40 miles per hour is twice as fast as 20 miles per hour, so it must be twice as destructive. That would be a reasonable answer, but it would be a wrong one. How destructive a car crash is its kinetic energy. That's why a car crash is destructive. A parked car isn't very destructive. That's not going to do anything. It's destructive because it is moving fast. And how much this is dependent on mass by a direct relationship, but by speed with a squared relationship. So if the speed is twice as much, that means the kinetic energy is going to be the square of that, 4 times as much. So a car crash at 40 miles per hour is 4 times more destructive than one at 20 miles per hour. How much more destructive is a car crash at 60 miles per hour than one at 20 miles per hour? It's 9 times more destructive. There's a square relationship. So the amount of energetic capability, the amount of work that something can do, goes up very rapidly as speed goes up. Speed's in there twice. So it's doubly as important as mass is. And that's something people always kind of forget about the kinetic energy equation. Sorry, I'm jumping around here a little bit. So, as we already expressed, work is equal to a change in energy. Right now, kind of focusing on just a kinetic energy, because we're not increasing height or whatever. It's only going to be a change in kinetic energy. They show you how this was derived from kinematics equation before, but we don't need to fuss with that. Total work is equal to the change in kinetic energy. This is what we refer to as the work-energy theorem. Anytime we say change in, remember it's always the final value minus an initial value. Final minus initial. So final kinetic energy minus initial kinetic energy. If we're starting from rest, this whole term gets to 0, and life is real simple. But also remember that work is also equal to FD. So F times D And really, this is just a kinematics equation. Remember those kinematics equations from a few chapters ago? This is just a kinematics equation rewritten a little bit different. So how much an object's kinetic energy goes up or down is equivalent to the amount of work done. And that's very much in line with what our definition of work is. Hold on, we'll come back to that example here in a second. So here's just a real simple example of calculating kinetic energy. Truck moving at 6 meters per second. Just plug and chug. Mass of the truck, square its speed. Okay, gets 70,000 joules. But the second part of that says, well, what's the kinetic energy going to be if we doubled the speed to 12 meters per second? We double the speed. I mean, you could replug it all in there or whatever, but you don't have to do that. You doubled the speed. Okay, double the speed. That means the kinetic energy is going to be 4 times greater, which is exactly what we see. We recalculate this here. We get 280,000 joules. That's 4 times as great as 70,000 joules. It's a guaranteed test question that there is a square relationship between speed and kinetic energy. So you have to understand how that proportion works. So here's an example using that work-energy theorem. How much work is required for a 74-kilogram sprinter to accelerate from rest makes it easy, to a speed of 2.2 meters per second? Well, work is equal to a change in kinetic energy. Change in kinetic energy equal to 1/2 mv final squared, minus 1/2 mv initial squared. V initial is 0, so that cancels out. And plug in V final, mass, square of V final times 1/2, 180 joules. Real simple. And as we already said, the sign of the work is related to change. Positive work means increase in kinetic energy. That's an increase in speed. Negative work has to mean a decrease in kinetic energy, which has to mean a decrease in speed. We don't need to fuss with that. So, moving on from kinetic energy, we can also increase something's energy by changing its position. You lifted a bowling ball from the floor up to the shelf. It had no ability to do anything down here. It wasn't going to hurt anybody. It wasn't going to fall on anybody's toe and break a toe. That's work. Crack the ground, break itself. Couldn't do any work down here. But it was at rest down here, and we moved it to being at rest up here. So it had no net increase or decrease in kinetic energy. But it still manages to have more energy. Now, it's just in a different form. The form that it's in is potential energy, gravitational potential energy. Up on that shelf, just by increasing its height, it now has the ability to do all kinds of things. To land on somebody's toe and break a foot, that's work. To crack the ground, that's work. To, crush a pop can or something, to alter something below it. Falls off that shelf, it's going to speed up and turn into kinetic energy. So it's stored energy. So by lifting it against gravity, we gave it the ability to do work. Now, how much work it can do when its height changes is found by this. Okay, PE, this is gravitational potential energy, you see down here, is equivalent to mass times the acceleration of gravity times the height above some reference point. We usually just use the ground to be that reference point. But that's also equivalent, as we see here, sorry, this stupid thing keeps showing up, to the amount of work done in lifting it. So see that underlined statement says the gravitational potential energy at a height equals the work required to lift an object to that height. So you lift something up, you did a certain amount of work on it, and stored that amount of energy in that object. And that work, that energy is going to be stayed stored there until something else happens, until it falls and turns back into kinetic energy or heat energy or whatever it's going to do. But this equation, you may also notice that it's kind of the same equation as the work equation, F times D. F times D, okay, F, M times G, that's weight. Okay, the work done in lifting it, you have to lift it, you have to apply a force equal to its weight, mg, F, times D, a height. Now this is not a distance, this is a height. vertical height. So if we go up a, incline or whatever, we don't care about the linear distance. We care about the height it gained. Something at the end of a long ramp up here has as much potential energy, and at the end of that long ramp, it will roll down that ramp and wind up getting to the same speed at the bottom of that ramp as if that object is just dropped from rest and allowed to free fall to the ground. I know that because as long as there's no friction or air resistance, both those objects have the same amount of potential energy. So I know that if both of those objects lose the same amount of height, they're going to gain the same amount of speed. So, gravitational potential energy. Here's like our third or fourth equation. Gravitational potential energy, go to M times G, still equal to 9.8 while we're on the Earth, times height. Easy problem there. Gravitational potential energy, 65 kilogram person, sitting on a diving board, 3 meters high. Not a problem. We also have things that have elastic potential energy. Okay, put it at the end of a rubber band or a spring. You compress or stretch that spring a certain amount. Again, we're changing its position. It gains a certain amount of energy. So think of like a spring-loaded gun or a slingshot, something like that. I'm not going to talk about that a whole lot now, but that's what we call elastic potential energy. And that's found by this equation, 1/2 kx squared. K is like the spring constant. X is the amount of compression or of stretching in it. But again, not something we're going to hugely worry on right now. But may want to read up on this slide again. We're on a spring. You compress or stretch the spring, or an elastic object. Energy is going to be stored in that. So that's a third type of mechanical energy. I know this thing up here is in the way, but conservation of energy really can be summed up. Energy can never be created or destroyed. It will only be transformed from one form to another. When we're talking about mechanical energy, it has to stay in some form of mechanical energy, as long as we are in a closed system. So, mechanical energy is equal to the sum of all forms of PE and KE. If there's no friction, there's no air resistance, or anything like that, that means that the total sum initially, PE plus KE initial, is equal to PE final plus KE final. This is another equation, conservation of mechanical energy equation. Now, the only time that this wouldn't hold true is that when there is some outside force acting, like friction, like air resistance. When that happens, you would add over here plus the work done by friction, or whatever that outside object is. So, if there's no air resistance, no friction, an object falls, starts at a height, has gravitational potential energy, it falls, it loses height, it gains speed. That's a general rule of thumb, right? When you lose height, you gain speed. When you're in a gravitational field, that's how that works. PE initial is equal to mgh. KE initial is equal to 0. PE final is equal to 0. KE final is equal to 1/2 mv squared. So here you wind up with PE initial is equal to KE final. And you could use that information to ultimately solve for V final or maybe a height, depending on what they gave you. So here's kind of an example. You have two slides, one straight, one curved. You can even say that one girl just dropped. Say you have a third girl here that was at the same height and then just fell into the water. If there's no friction on this slide, all three girls would enter the slide with the same speed, because all three girls lost the same amount of potential energy, which means they all gained the same amount of kinetic energy, which means they're the same mass, they all gained the same amount of speed. So the path does not matter. What matters is the height lost. Okay. I'm going to pause for right there.